Okay, when we left off, we were talking about voltage sources and loading and things like that. And we said that when we left off, that an ideal voltage source was a voltage source that would put out the same voltage, the rated voltage, regardless of the load, except unless the load was zero. So in other words, if the load resistor was 1 ohm, we'd still see 9 volts over here. If it was 100 ohms, we'd still see 9 volts. If it was 1,000,000 ohms, we'd still see 9 volts. If it was 0.1 ohms, we'd still see 9 volts. So whatever this rated voltage is, with an ideal voltage source, that's what we would get out. And we said that in an actual voltage source or a practical voltage source is internal resistance. And if you think about it, there has to be. There's wires that connect from the battery, the chemical elements themselves, to the terminals. The wires have resistance. Within the chemical elements themselves, they're made up of metal and other materials that have resistance. So there has to be a certain amount of resistance that if we take all of that wire resistance and the resistance in the chemical elements and everything, put that all together in one lump sum, we call it RS or R internal, there has to be some resistance in an actual voltage source. Which means that if we look at it that way, the minute I stick a resistor over here, meaning we are using it to power something like a load, that means I have 2 resistors in series. That forms a voltage divider. So that means that not all of this voltage that we got over here, the ideal 9 volts, would make it over to here. Some of it would be lost across the internal resistance. And we said the bigger the bigger the load is, the closer you'll be to the actual or ideal voltage. So we said that with a DMM, if I connected up a DMM, which looks like roughly 10 mega ohms, I would probably leave, and it was a 9-volt battery, I would probably read close to 9 volts, very close to 9 volts. But if I put a lamp on that 9-volt source, then I would probably read a much lower voltage because we'd now start to draw more current. And if you think about here, as I draw more and more current through this resistor, the voltage that's lost across this resistor, that's dropped across the resistor, gets to be bigger and bigger. V equals I times R. If you make I bigger, the product has to be bigger. That means that you start out with the same, let's say 9 volts, and you lose more, means you've got less over here. So that if I draw a fair amount of current with like a light bulb, you know, a 9-volt or an 8-volt or a 10-volt bulb, we'd see that the actual voltage that we measure across the bulb would be considerably smaller than 9 volts because we've lost the difference between this voltage and this voltage gets lost in the internal resistance of that battery. So that's pretty much where we left off. Now, there's a corollary to that, and that is the current source. If we think about a voltage source, we know what the ideal voltage should be, but we don't know what the current is. So in other words, if I handed you this source and said to you, what's the current flowing? You'd tell me it's 0 because it's not connected to anything. And then if I connected up the DMM or I connected up the light bulb, the amount of current that we measure would be varying depending on what the load is. So the load determines what current flows out of the voltage source. Well, in a current source, we're saying that the ideal current is specified. Hold on, I gotta let somebody in. And the voltage across the load will vary or will change to provide that current. And the symbol for a current source is a circle with an arrow. And for an ideal current source, will output the specified current regardless of the load.
How does current source look like in real life? Voltage source is a battery, voltage supplier, but how does it look like?
It doesn't. There are some benchtop current sources. A lot of times what we primarily use the current source for is as a modeling device. When you get into ELT113 next semester, you're going to see that the model for a transistor is going to have a current source in it, because the idea of a transistor is you put a certain amount of current into the base, the transistor multiplies that current, and that current will come out of the collector lead and will come out regardless of the load within the range that the circuit will allow. So there really isn't an actual widely, let me put it that way, widely used current source. There are some benchtop instruments which are current sources, but they're not widely used. Primarily we use voltage sources. The biggest thing we use current sources for is in modeling stuff, both bipolar junction transistors and junction field effect transistors and MOSFETs are all modeled using current sources. So
Okay.
the exception, let me just finish this up. The ideal current source will output the specified current regardless of the load, except for RL is infinite. Just like we said that you couldn't have a voltage source that puts out the specified voltage at 0 ohms, we can't have a current source that puts out a specified current at infinite ohms. It's an open circuit. So in other words, if I had this for an ideal current source, if I had, let's say this is specified as 100 milliamps. Well, if I put an ammeter over here, remember ammeters go in series, and I have a load resistor, and let's say this is 1 ohm, this is going to read 100 milliamps. If I had that same 100 milliamp source, I had my milliammeter, and this is a load of 10,000 ohms, 10K ohms. This is still going to read 100 milliamps. If I had the same
for this, you need a huge voltage.
Yeah, it would, but it would adjust automatically to do that. And 100 milliamps is a really huge number. Well, you need 1,000 volts to get that to happen. But the bottom line here is that if this is an ideal current source, these are ideal current sources, no matter what value I make this resistor up to infinite, theoretically, this current source is going to put out the 100 milliamps. Now, in reality, for a practical example of a current source, and let me go back to one of Ronnie's questions before, and it tied into what we talked about yesterday. If I go back to here and I talked about the voltage changing because of the internal resistance, you have to remember that benchtop instruments like your Harrison power supply that you use in lab, or Hewlett Packard now, what Harrison, but anyway, the power supplies you've got that you use in the benchtop, those are auto-correcting power supplies. So they actually measure the output voltage and know what the reference voltage should be and will automatically change to create a constant output voltage. So not all bench power supplies do that. If you buy a cheap power supply, it can vary. But if you're buying a lab quality power supply like the Harrisons are, if you set that for 6 volts, it'll stay at 6 volts over a very, very large current range. If you set it for 10 volts, it'll stay at 10 volts, regardless of the load you put on, within reason. One quick story related to this, and it's a really important one. Whenever you use a power supply, especially if it's a cheap power supply, like a wall wart that powers your phone or whatever. I read a story, an article about in Nuts and Bolts magazine, and if you've never seen Nuts and Bolts magazine, there's some of them floating around in the lab. A guy was working for a company that made something, I don't even remember what the something was, and it was powered by a wall wart, plug-in brick that plugs into the wall, and you got your cord that goes over. So his company shipped out 10 of whatever it was to the company that they sold them to. And they arrive, and all of a sudden they get this phone call that none of them work. And they went, okay. So they ship one back, and sure enough, something on the input was blown. So they ship all the rest of the 10 of them back. They rebuild them. They ship them back. And they get the phone call, these don't work either. So finally, they rebuilt them again and sent a rep out with them. And the bottom line was there was nothing wrong with the unit they had built. What they had was a condition where, when we talk about power supplies, and this is worth writing down, if we talk about a power supply, you'll talk about two things: the no load voltage and the full load voltage. The no load voltage, when we talk about the load, we're talking about the load current. So the load current, there's no load, so the load current is equal to 0. Okay? The load current is equal to 0. And I thought somebody was saying there might have been somebody in the waiting room, but there isn't. The full load voltage is the voltage with the max rated load current. So what the story was they had this wall wart that was rated at like 9 volts, 9 volts at 1 amp. The problem got to be that when you plug this in without it being connected to anything, it developed a no load voltage close to 16 volts. Once you started drawing current from it, it dropped down to 9 volts. But so they plugged the power supply in, it generated 16 volts. They plugged it into the unit that it was supposed to power. That unit didn't want to operate above 12 volts. So the minute it got hit with 16 volts, the no load voltage, it popped whatever it broke inside the unit. So the bottom line is that whenever you've got a, by the way, this is for an unregulated supply. All right, we talked about the lab benchtop power supplies. Those are what we call regulated supplies because it regulates the output voltage to whatever you set it to and adjusts and makes the adjustments to keep it at that. But an unregulated power supply, like you might find like on my tablet, this has undoubtedly an unregulated power supply. Their case was that the no load voltage is going to be higher than what you want it to be. And then when you pull a load current from it, it drops it down to whatever is supposed to be. Next semester in ELT113, you're going to build an unregulated power supply. I don't know whether or not they'll actually do a no load and full load test. But one of the things that we talk about is the voltage regulation. And you're going to talk more about this next semester. I'll spell it right. And that's going to be an indicator of how much this variance is between no load, meaning no load current, max resistance, and full load voltages. And the voltage regulation gets to be a pretty critical thing. It's a number where less is more because it looks at the difference between these two divided by the full load rating. Anyway, bottom line is that the benchtop supplies are regulated. They hold the voltage to be constant with a circuit inside that makes the adjustments that as the current increases, normally the power supply would want to drop in the output voltage. It automatically makes adjustments to keep that as a constant. Unlike a battery, which is an unregulated supply, when you start to pull load resistance, load current, you lose voltage across the internal resistance. Okay, so back to current sources. So in a practical current source, what we really have is that same issue of internal resistance, except now we draw the internal resistance in parallel with. All right. So that would mean that, let's look at where that impacts us. So let's say that, no, let me, somebody's got to come in. Hold on. Oh, before I forget, and I meant to tell you this at the beginning, Professor Atwood has the exam too. And on Thursday in lab, I believe he's going to go over the exam. If not that, at least he'll give you the exams back. So you'll be getting back the exams. I dropped them off. The last person who needed to took it. You'll be getting the exams back on Thursday. Okay. So for a voltage source, the ideal voltage source looks like if my internal resistance was here, for an ideal voltage source, if we went up here for a minute, the internal resistance is going to be 0. All right. So that if I have nothing in series, then I don't have any resistance to drop voltage across. If this was 0 ohms in this leg, then I have nothing to drop resistance across. It would always stay the same 9 volts in this particular case. In a current source, the ideal current source would have the internal resistance is infinite because it's in parallel. So if I take this out and make it infinite, that's an open circuit. That's the same as I've got over here for my ideal source. So let's say, for example, I have a current source, looks like this. And let's say the R internal is 100K. And let's say this is 10 milliamps. Well, if I hook up a resistance over here, a load resistance, if RL is 10 ohms, I sub load, remember the current divider formula, we said that for current division, IL is going to be the other resistor. So if I want to find the current through this resistor, I use the other resistance, R internal, over the sum. And we multiply that times IS. So for this example, it would be 10 ohms, 10K, 100K over 100K plus 10K times 10 milliamps. So IL is going to be 9.09 milliamps. Oh no, that's, oh, hold on. It's going to be much better than that. Forgot that's not a K. So 9.999 milliamps. All right, which for all intents and purposes is 10 milliamps. It hasn't changed. Let's say we went to 10K. So if this load resistor was 10K, then we get the 9.091 milliamps I just calculated. And if the load resistance was 100K, then we would have 5 milliamps. So the bottom line here is we want this internal resistance to be very, very large compared to the load. So in a power voltage source, we wanted the internal resistance to be small. In a current source, we want the internal resistance to be as big as possible. Okay. So we've got two different circuits. two different ways of looking at sources. There's current sources, which again, we use primarily as a modeling tool. You're going to see when we look at it in a transistor circuit, we'll use a current source. And for most practical applications, we always look at a voltage source because that is what we've got. Okay, we can make batteries very easily. We can make power supplies that are voltage sources very easily. Current sources, not so much. Questions about either voltage sources or current sources before we go on to the next step? Okay. Hearing none.
Sorry.
Yeah.
One question. So for the ideal current source, it's a like R is going to be like infinite.
Yeah, ideally, this is infinite because remember, if this is the ideal current source, looks like that, right? This is an ideal current source. If I make this infinite, an infinite is an open circuit, right? So an open circuit would take this resistance out. And if I take this resistance out, I'm left with this.
Okay.
So yeah, the bottom line is that the internal resistance wants to be infinite in an ideal current source.
Okay.
Clear up a little?
Yep.
Okay.
Thank you.
All right. So sometimes what we want to do is we want to be able to say, I have a circuit that's got a current source in it, and it would make analyzing the circuit a lot easier if I had a voltage source. Or I have a circuit that's got a voltage source in it, and it would make analyzing the circuit a lot easier if I had a current source. So one of the things we want to do is look at source conversion. So let me do it this way. I always find this works pretty well. We have RS, we have VS, and I want to maybe get RS and IS. Okay? Now, in order to get the value of IS, we want to find in this circuit what's called the short circuit current. Which is exactly what the name implies. It's the current when the circuit is shorted. So if I went over here and I stuck a short over here and I said how much current is flowing over here, we'd find out that I short circuit is just VS over RS. And it turns out that that's the value that we need for a current source. So if I'm going from here to here, I can say that I sub S over there is just V sub S over RS. So I would take the V sub S, divide it by the R sub S to get the value of R, I sub S over here. VS over RS gives me this current. The RS is equal to RS. So I take the RS value and that becomes the RS value. Okay. Over here, if I want to go the other way, what I'm looking for is the open circuit voltage. Well, if I have an open, that means I've got nothing connected over here. The IS only has one place to go, and that's through the RS. So I can figure out that the V open circuit is going to be I sub S times R sub S. And that also happens to be the value of the voltage over here. So if I want to go from a current source to a voltage source, I would say V sub S is I sub S, R sub S. This I sub S, this R sub S. And let me get this short out of here before it confuses people. So now we got the value of V sub S. And if I wanted the value of R sub S is just equal to R sub S. So we take that value, becomes that value. So for example, so if I had this, V sub S is 6 volts, R sub S is 2 ohms. And we want to convert to a current source. I sub S is VS, over RS. So I've got 6 volts divided by 2 ohms, 3 amps. So that means that over here, my current source is 3 amps. We need the RS value, so we went this way. The RS value two ohms. Theoretically, it says it's an equivalent current source. That means that whatever load I hook up over here, I would get a certain voltage and a certain current. If I hook that same load over to this equivalent current source, I would get the same voltage and the same current. So let's see whether or not that's true. Let me put a new sheet up. And move that over to here. So what did I have? I had And let's do this. Let's connect up keep the numbers simple. 8 ohm resistor, and we'll connect up an 8 ohm resistor there. I'm saying that what's inside this box and what's inside that box are the same. So in other words, if I had a box and I said to you, hook up an 8 ohm resistor to the box and tell me, is it this circuit or is it this circuit? You wouldn't be able to do that because they're equivalent as far as anything out here is concerned. Whether I've got this hooked up or this hooked up, it's going to behave the same. If I change this to 100 ohms and change this to 100 ohms, change this to 100 ohms, all three would read the same because you don't know what's inside this box. Could be this circuit, could be this circuit. So let's figure out and see whether or not that's true. We could very easily say, let's call this RL. We could say V sub RL is going to be RL over RS plus RL times VS. Use voltage division. So we've got 8 over 2 plus 8 times 6. V sub RL is going to be 8/10, 4.8 volts. No, yeah. And if I wanted to, I sub RL is V sub RL over RL, 4.8 volts divided by 8 ohms. 0.6. So that means that if these two circuits are truly equivalent, then when I do my calculations on the right-hand circuit, these are the two numbers I should come up with. So let's, in this case, find the current first. So I sub RL, we take the other resistor, RS, put that in the top, and divide it by the sum. That was current division. And we multiply that times I sub S. So I've got 8 over, excuse me, I've got 2 over 2 plus 8 times 3 amperes. I sub RL is 6 divided by 10.6 amps. And V sub RL is I sub RL times RL, 0.6 amperes times 8 ohms. 4.8 volts. So we can see that when we put an 8 ohm load on, the voltages at the output are the same, the currents at the output are the same. Just to verify this, what I'd like you to do is do the following. Let's go up by a factor of a little over 12 times. If this was 100 ohms and this was 100 ohms, do the calculations and see whether or not the voltage and current over here and the voltage and current over here are the same now that we've changed the resistor values. I'll give you a couple of minutes to try to work on that. When you come up with your answers, text me your answers in the chat. Anybody have numbers yet? I haven't seen anything come up in chat. So once you come up with the two answers for each circuit, All right, so I'm not going to rewrite all the formulas. What I'm going to do is I'll just put them in a different color and put the numerical part. So over here, the formula stays the same, except this now numerically changes to RL is 100 over 2 plus 100 times 6 volts. So the VRL for 100 is going to be 5.882 volts. And now the formula stays the same. So IRL is just going to be 5.882 volts divided by 100 ohms. So I sub RL is 58.82 milliamps. Don't round. One thing that you can get yourself into a whole boatload of problems. This worked out to be 0.60000, so I wrote it as 0.6. But don't round this up, because later on, if you do calculations with that number and it's rounded up, I think our rule of thumb was work to 4, round to 3 for your final answer. It gets rounded to 3. Everything else hold 4 significant figures. If I go over here, now the RS is still 2, but now the RL is 100. So now this just becomes 2 over 2 plus 100 times 3 amperes. So the IRL for the new value of RL is 58.82 milliamps. And VRL is going to be 58.82 milliamps times the RL is now 100. VRL is 5.882 volts. So again, the RL's matched up, 5.882 in both cases. The I loads matched up in both cases. So that means that what's inside of this box is equivalent to what's inside of this box as far as anything outside the box is concerned. You would not be able to tell the difference. In other words, if I handed you this and said, whoops, and said this voltage is 5.882 volts across RL, what's inside? Is it the practical voltage source, or is it the practical current source? You wouldn't be able to tell as far as anything out here is concerned. That's what the word equivalent is all about. It means that they're the same. Okay, so source conversion, and we go from voltage source to current source, or current source to voltage source, either one. And once we've done that, we've got two equivalent circuits. Let me just, okay. All right. Questions on any of this stuff? So on Thursday's quiz, if you had this converting a voltage source to a current source or a current source to a voltage source, actually this, we'd be good? Or are there questions? Okay.
I think we'll be good.
We'll find out on Thursday on the quiz. So the whole idea here is that this circuit over here is equivalent to this circuit over here. This voltage source, practical voltage source, and this practical current source are equivalent. Put them in a box. From the outside of the box, you can't tell which is inside. All right. There's another circuit that we use. Was there a question before I go on?
Nope.
Okay. There's another source that we're going to look into. Our book does, in chapter 8, does superposition and then comes back to Thevenin. I'm going to do Thevenin first because it sort of ties in with the whole idea of equivalent circuits. So what Thevenin's theorem says that any linear circuit so for our intents and purposes, that's a resistor circuit.
Professor,
Yeah.
I have one question. The quiz is going to be on series parallel circuits.
No, I didn't say that. I said it's going to be on source conversion.
Oh, got it.
So Thevenin theorem says that any linear circuit can be reduced to an equivalent circuit comprised of a voltage source in series with a source resistance, or just a resistance. So what that's saying is we can take this big complicated circuit and reduce it to the Thevenin equivalent circuit. And since that's way too much to write, we'll just always abbreviate that as TEC, which looks like this. So what we're saying is what's ever in this big complicated circuit that's connected to the load, I can reduce this circuit down to a V Thevenin and an R Thevenin in series inside of this box. And as far as the load is concerned, it doesn't know whether the Thevenin equivalent is in the box or the big complicated circuit is in the box. All right. Now, having said that, Thevenin's theorem is an analysis tool. I wouldn't design this big complicated circuit and reduce it down to a voltage source in series with a resistor. Why would I develop this big complicated circuit if I knew, and the bottom line was I could just replace it down to this? Why don't I design this in the first place? Okay, so the whole idea of Thevenin is we're going to take this big complicated circuit and reduce it down to a simple circuit. So when I analyze, so one of the things, let me give you an example. One of the things is we might have an amplifier. Could be an audio amplifier, could be an RF amplifier, could be whatever. So we got this big complicated amplifier circuit. And we say, well, wait a minute. How does this circuit behave if I connect up a 100 ohm load resistor? So I'd have to go through these big, long, complicated calculations to figure out what the voltage over here is with 100 ohms. And then I say, but wait a minute. What about if we make this load resistor 500 ohms? What does that do? And then you go through these big, long, complicated calculations again to find out what it is at 500 ohms. And you see, maybe it's moving in the direction you want. So you say, oh, wait a minute. How about if we make this 1,000 ohms? So you go through these big, long, complicated calculations all over again to figure out a load, the load voltage. And then somebody says 2K. How about we do it at 2K? And then you throw an eraser at them or something, because you've been through these complicated calculations 3 times already. The whole idea of Thevenin is I do this big, long, complicated calculation, or maybe not even so big and long, but a complicated calculation to figure out what V Thevenin is and R Thevenin is. And if this is equivalent to this, then no matter what load I hook up over here, I'm just doing a voltage divider calculation to figure out what the load voltage is. So you take some time up front to look at the big complicated circuit, say, okay, let me calculate V Thevenin, let me calculate R Thevenin. Once I've got that, hey, tell me what you want over here. And I'll do voltage divider between these two across this resistor. And I'll come up with your load voltages like that. Okay? So that's the whole idea behind Thevenin. It's an analysis tool. All right? We don't design a circuit, like I said before, we don't design a circuit, then reduce it down to this, and then go do whatever it is. It's like, why didn't we just design this in the first place? But it is an analysis tool that allows us to do a what if RL is this value? What if RL is that value? What if RL is some other value? And very easily come up with the value of the voltage across RL, as opposed to redoing complicated circuits 3, 4, 5 times. Okay? And we're not going to get to Thevenin in 7 minutes. So let's stop here. And what we'll do is we'll start with Thevenin next time after the quiz. All right, so on Thursday, we'll do the quiz and then we'll get into Thevenin. How do I calculate a Thevenin? How do I find V Thevenin? How do I find R Thevenin? What I can do is, yeah, I'll wait. How do you calculate V Thevenin? How do you calculate R Thevenin? How do I use the Thevenin equivalent circuit to find whatever I want? All right. So, yeah. Any questions? That's what I was going to start with next time. Okay.
So I have a question.
Sure.
If you want in the design stage, let's say that you have constraints of resistors, like you have resistors that can only, they're 0.5 watts resistors.
Right.
So, and let's say you have 1 ohm resistors and you need 10 ohm, but a resistor that can get rid of this amount of energy at that time.
Yeah.
At this amount of time. So actually you do want to use more resistors than just Thevenin.
Oh yeah, but like I said, the Thevenin is an analysis tool. We wouldn't, yeah, you wouldn't want to design a circuit and then reduce it down to Thevenin and then just build the Thevenin equivalent. The Thevenin is strictly a mathematical tool. So in other words, if I gave you, hold on, let me show you exactly what I was talking about. I have to share a different screen. This is actually a circuit we're going to look at. So forget about the circuit on the right. Let's look at the circuit on the left. Okay. I need to, yeah, because the circuit on the right's entirely different. Let's say, let's eliminate that. Is this running? Oh. Okay. There we go. Let's say this is my load resistor. okay? And I wanted to figure out what's the voltage across this resistor. But I want to be able to do it when this is 3.9K and when it's 4.7K, when it's 10K, when it's 100K. I would have to go through this big, long calculation of calculating the REQ, then working my way back out, finding voltages and currents till I got to here. And I'd have to do that over and over and over again for the voltage across this resistor. What I'm saying is Thevenin allows us to take all of this stuff and get rid of this and get it down to one resistance that this resistor is going to connect to that's in series with whatever the Thevenin voltage would be. So we have to figure out, so what that's going to reduce to is a voltage source, a series resistor, and the load, so that I don't have to redo that complicated calculation over and over again. It's strictly an analysis tool.
But you won't be doing that if all the resistors are actually applications in the circuit. I mean, let's say R1 is a motor and R2 is a resistor that's supposed to reduce the current for an LED.
No, yeah, but not, yeah, but let's talk about an amplifier. All right, so if I have an amplifier, I might be concerned with, if I hook up an 8-ohm speaker, how much voltage and power do I get out for a given input signal? If I have a 16-ohm speaker, how much voltage and power do I get out? If I have a 32-ohm speaker, how much do I get out? If I have a 4-ohm speaker, how much do I get out? So think about this as like the speaker. And all of this amplifier stuff, and this is obviously not an amplifier, but all of this amplifier stuff in here, I don't need to calculate in the amplifier the gain of the first stage, the gain of the second, the output voltage of the first stage, the output voltage of the second stage, the output voltage of the power stage, when I can reduce all of that down to one equivalent AC source and one equivalent series resistor that I can now connect up to a 4-ohm resistor or an 8-ohm resistor or a 16 or a 32, whatever ohm resistor I got, representing the load, the speakers, if you will.
Okay. So
Okay,
this
so
is just to figure out what will be the voltage and what kind of resistance that resistor will see if you connect it to all that circuit.
Exactly.
Okay.
So envision that this is the amplifier circuit, and I don't really care what's going on inside from stage to stage to stage. All I care is when I get to the output, what's it going to do? And I can do that by reducing the, down to the Thevenin equivalent and hooking this load up to the Thevenin equivalent, and I would get the exact same output as if I did all the long calculations to get to here each time.
Okay.
Pretty powerful tool, actually. Okay, any other quick questions? Okay, if there are no questions, I'm going to stop the recording.